Hello and welcome to Maths on the Move, the podcast from plus.maths.org. I'm Rachel Thomas. Recently, we've welcomed an exciting new addition to the Centre of Mathematical Sciences at the University of Cambridge, which is our home at plus.maths.org. And our new neighbour is the Centre for Climate Repair. In this podcast, we talk to its director, Shaun Fitzgerald, about the Centre's work, its recent contribution to COP28, and what all of this has to do with maths. The fundamental problem, of course, is that greenhouse gas levels are too high, therefore temperatures are too high, and the rate at which they're rising is just out of control. The mission of the Centre for Climate Repair is to get greenhouse gas levels down, but also to provide options for society so we don't lose precious ecosystems and the precious ice covers in Greenland or Antarctica, which could lead to worldwide devastation. Here is Shaun, in conversation with my colleague Marianne Freiberger, explaining more about the Centre's core missions: reduce, remove and refreeze.
So we've got to do three things. The first is to obviously reduce emissions. The second is to remove greenhouse gases from the atmosphere. And then the third is to buy us more time, is to what we call refreeze. And that means looking at other options whereby we can just protect the Earth, for example, by reflecting more of the sun's radiation away from the Earth before it has a chance to actually heat the Earth. So that refreeze piece is sometimes called geoengineering. We call it refreeze.
Geoengineering is something that people are sometimes a bit frightened of. Is there anything you'd want to say to address that when people are scared?
It's a really important thing to raise, because the term geoengineering, which was coined a while ago, does solicit sort of certain reactions from people. It's a term I don't particularly like, to be honest. I prefer climate interventions or climate engineering. And one of the approaches that has been associated with the term geoengineering for some time involves in the injection of stratospheric aerosol injection, so injection of particles into the stratosphere, such as sulfur dioxide, to then create droplets of sulfuric acid that then reflect some of the sun's radiation back out to space. It's a process that goes on with large volcanic eruptions anyway. And the question is, well, what about the good bits of a volcano? There are lots of bad bits, don't get me wrong, but are there some benefits to those sorts of things? And then another one, which is, for example, the influence of shipping. Right now, we've seen a change in the fuel mixture that's being allowed to be burnt by ships as they traverse the ocean. It's cleaner, and from a health benefit, that's a good thing. So ships near the coast, when they've been emitting sulfur dioxide and other things into the air, yes, there are air quality issues associated with that. But when they're way out in the middle of the ocean, the particulates and things that get ejected from a ship's funnel, they don't make it onto the land. And yet, that sort of fuel mixture has been helping reflect some of the sun's radiation back out to space. So as a result of the change in the shipping regulations, we're now seeing the Earth a bit warmer than it was before. So previously, we were inadvertently doing geoengineering. Gosh. Well, should we even consider reversing some of those shipping regulations, not near land, but out of the middle of the ocean? And these are valid questions that are posed not just by me, but they've been posed by, the founders of Extinction Rebellion. There's a blog post on the 19th of October 2023 with Roger Hallam, Gail Bradbrook, and they posed the question, should we even review those regulation changes? Were they all a good thing? Question mark.
So it's a need for holistic thinking, really, and taking everything into account.
Absolutely. And it's a need for an openness of mind. I'm not suggesting that any of these are necessarily good things. I am saying, though, that we need to do more research in this area and further our knowledge with all of these to understand with greater clarity what the benefits are, what the cons are, and what would be involved if ever you were to scale them up. And we need to do all of this work at pace so that society has options that it then can consider. The idea of just rejecting, let's say, use that horrible term geoengineering, the idea of rejecting it because it sounds scary right now, in large part, I think it's scary because we don't know enough about it. We're all scared of things we don't know a lot about. So we need to go and build a knowledge base with much greater clarity at pace. We need to do that urgently so that we can then make more informed decisions as to whether there are any, let's say, geoengineering approaches that we think might be sensible for society to at least consider.
Now, you went to COP28. What did you contribute there?
So, there are three areas, I think, that are important to think about the way a COP is structured, for those who are not necessarily familiar with the COP. There is, number one, the negotiations between the different countries as to what gets agreed, what doesn't get agreed, whether it's money and things like that. That's actually now a relatively small part of all of the people that go to a COP. The next piece, which is where I contributed most, is a group of interested parties, scientists, NGOs, faith groups as well, in the rest of the Blue Zone, with events, sharing thoughts, challenges on, for example, even things like climate engineering. And I was involved in the Blue Zone on a number of events discussing all of these issues. And we had divergent views, but they were robust conversations, but they were constructive. They were not sort of antagonistic. And sometimes you hear about these sorts of interactions going on. Absolutely not in the COP Blue Zone. So it was healthy debate. And then there's a green zone, which is more for the public, the wider public, to be able to access and learn more about some of the issues. So there's more of an educational piece. I was mainly involved in the science discussions in the Blue Zone.
Mm-hmm. And are there any messages you took away, other than maybe the obvious that we all read about in the paper, but anything that struck you particularly?
Well, there are two. The first is actually on the negotiations. It's amazing, that in an oil state hosting a COP, for the first time, it was then agreed by all the parties in writing that we must transition away from fossil fuels. I mean, let's be honest, it's taken 28 COPs, nearly 30 years to state the obvious. So that's sort of the flip side. But let's give progress recognition for what it is. But the second is that for the first time there were multiple groups wanting to engage and talk about the field of climate engineering and having meaningful discussions, and I found that incredibly healthy about the vibrancy of the debate. And I learned, particularly there was one speaker from she was the United Nations ambassador for the islands of Palau. That's a group of islands in the Pacific Island and in the Pacific Ocean, and they are atolls. And she said, the idea of sea level rise of 1 or 2 meters for my people is not losing a bit of beach. It's losing our country. My people will have nowhere to live. And her message was that if we're just going to continue to only think about, and it is realistically only think about at the moment, emissions reduction and greenhouse gas level reduction, we haven't reduced greenhouse gas levels, period. We are reducing the rate at which we are increasing greenhouse gas levels. So that's a positive thing. And she said, if that's all that we're going to be talking about, and yet there are things such climate engineering options that we could be exploring, such as seabed curtains or ice thickening or solar radiation management. She said, my people want to see that research progress that pace so that as a global society we might have some more options. She was not keen to hear that people saying we should not be researching this space. She said, Who are you to be saying that we shouldn't be doing this? Think about my people, listen to my people. And some of these minority voices need to be amplified because they need a big seat at the table. And that's the biggest thing that I took away.
How important is public engagement then, and fostering, nurturing public discussion and debate?
Incredibly so. And it is very, very important that we have open conversations where we're not judging whether it's a good thing or a bad thing. People might have their views, and at the moment I don't have views on whether it's a good thing or a bad thing, because at the moment I think there's a lack of knowledge. And when I hear for a preservation of a paucity of knowledge rather than a call for a furtherance of knowledge, I'm definitely in the latter camp, as you would expect me to be so as an academic from the University of Cambridge. Furtherance of knowledge is one of the key tenets of being part of a university. But sharing the openness of mind and the challenges that are associated with this research, because there is this thing called the moral hazard, that if you do even research in this area, does it then encourage people to ease off the accelerator on the energy transition? Well, I'm not sure I completely buy that argument, but it's just because of the history of the last 30 years. People haven't been not working hard enough on reducing emissions because of the prospect of things like climate engineering. They just haven't been doing it.
Are there parallels from other fields, medicine or something, that people stop striving for something because there is another type of intervention on the horizon? Are there other fields?
There are, absolutely. And what's really important that we should learn from other areas of science and development. So, for example, medicine, drugs. So, what about healthy eating? What if we were to develop drugs that actually help moderate how much food you take and things like this? So there is literally research, and there have been people saying, no, you've got to cure the cause. So you're not going to operate or give people healthcare because they're not living a healthy lifestyle. And generally speaking, the furtherance of knowledge. At the moment, we're not offering drugs. We're not offering the climate engineering drug to the world. We just want to know more about these things, which might show that some of these things are actually nuts. Right? They actually know that the potential challenges associated with this might well be rather greater than the benefits that were originally proposed.
So coming to your team, to your Centre for Climate Repair, can you describe it? How many disciplines are in it? How many people are working together? How are they working?
So it is a multidisciplinary team, and first of all, and it's multi-institutional. So what's really important is that any particular approach that we are exploring, especially in the refreeze area, but similarly in the remove area, those are the two R's that we're really focusing our research on within the Centre for Climate Repair. They involve the social sciences, they involve the physical sciences, they involve engineering, they involve also people from the Judge Business School, for example, looking at what is it that not just behaviours, but if there is a business behind this, how do you go and think about financing carbon credits in the greenhouse gas removal space? So very multidisciplinary. But what I find particularly stimulating about the nature of the projects is that, great though Cambridge is, Cambridge doesn't do everything, and Cambridge doesn't lead on everything by a long way. And it's being part of a global consortium in all of these projects, and figuring out who in that consortium might be best placed to lead a particular approach or a particular project. And I have this fundamental belief that you put a group of really brilliant people together, and although you may have been the convener, you might not be the right person to then go and lead a particular project. And the right person is often going to be nominated by the group. He or she or they will emerge from the group. And that's what I'm finding particularly stimulating working in this area. which is relatively new for me. So I haven't spent my whole career on remove or refreeze. I've spent nearly all of my career in the reduce area. So I'm enjoying this this foray.
Could you give me a particular example of a project that people are working on? And
so one of the smaller projects that we are involved in is what we call ice thickening. So this is a project where we are exploring whether it's possible to grow more sea ice in the Arctic winter in order for the sea ice to last longer over the Arctic summer, and therefore maintain a greater areal extent of ice over the Arctic. And that's fundamentally really important because ice is pretty reflective and the dark ocean is not. So if we can reflect more of the sun's radiation in the Arctic summer by having a greater area of ice cover. So
how do you do that? How do you thicken it?
How do you thicken it? So you've got to try and get more sea ice to grow in the Arctic winter. And fundamentally, that means trying to radiate more heat out to space in the Arctic winter. And the way that happens normally is that as ice grows, so it's freezing on the top of seawater. So the surface temperature from which one is radiating heat out to space is, for example, minus 20 degrees centigrade. And yet, if you were to pump seawater on top of sea ice, let's exclude the effects of salt for the moment, then the freezing temperature is 0 degrees centigrade. Therefore, the temperature of the surface from which you are radiating heat out to space would then be 0 degrees. So you've raised the temperature at which you are radiating heat out to space, and therefore with black body radiation, you're going to go and radiate more heat out to space. So how do you do this? The idea is exploring whether it's possible to pump enough seawater on top of sea ice and increase the rate at which you form the sea ice. That's one of the projects. And we are working with scientists here in the Department of Applied Mathematics who are expert fluid mechanicists and understand heat and mass transfer, and also understand the phase transition between water, ice, and indeed seawater and sea ice. So there's a body of knowledge here with Professor Gray Worcester, which is just unparalleled. It's just wonderful. But we're also working with an outfit called Real Ice. They're a not-for-profit company who have already been doing some field trials and doing public engagement in the Arctic. And there's another group called Arctic Reflections who are based in the Netherlands, and they're also supporting this overall initiative, looking at a slightly different method between Arctic Reflections and Real Ice. So it's not a huge consortium, but that one project alone involves multiple parties offering different skill sets.
And then one of my questions was going to be what's the role of maths, but yeah, so it's obvious that there's fluid dynamics in there, like you said, there's phase transition stuff in there. In other projects you might have other types of maths that just kind of pop out as being hugely important apart from fluid dynamics.
Well, maths is germane to all of this. So one of the other projects that we're looking at is marine cloud brightening. It's exploring whether you can make clouds that form over the ocean in the marine boundary layer, so let's say 1,000 meters up, whether you can make them brighter. And what that means is whether you can get the clouds that form to be comprised of more smaller droplets rather than fewer larger ones. In other words, that's for the same.
Is that for reflection as well? Yeah.
That's for the same water vapor content, and clouds that are formed of more smaller droplets are whiter because of the relationship between the droplet size and the wavelength of light. So they are optically brighter, and therefore they will reflect more of the sun's radiation. Now, where does maths come in? Well, the maths comes in multiple ways. The first is helping understand the way that droplets form. But at another scale, which is another part of maths, which is to do with the interactions between the clouds and the aerosols, or the clouds and the little particles that you're forming, which are then relatively dry. And that is atmospheric modelling. So that's a completely different area of maths, and hence people like Peter Haynes are here in the Department of Applied Mathematics, but we're working with a group down in Exeter as well who do numerical modelling. But it's a different kind of mathematical modelling approach that we're looking at. And that one project draws in lots of different areas. And then there will be a further area of maths, which is then looking at the particular strategies that you might then deploy for marine cloud brightening. If you're using existing ships, for example, and figuring out which of those ships and how much should their journeys be adjusted to go and increase the effectiveness for marine cloud brightening, there's going to be machine learning being applied. There's a whole other area of maths. So
that would be applied in order to figure out
which ships might be used, which ship journeys, if you can then go and harness some of the existing fleets once the technology's been developed.
So they would then make whatever needs to happen to make the clouds brighter.
And in fact, I would go so far as right now, those existing ships, if I go back to the bunker fuel, they're already causing marine clouds to form and for them to be brighter. So even without any technology, might we even consider the existing flotilla worldwide that we have,
machine learning
and then
to understand the
exactly,
data
and use machine learning to help inform what you might even do with existing infrastructure, and then how might that existing infrastructure be supplemented with any technology that we develop, and then there's maths is everywhere.
Now I'm tempted to ask you for another example. Is there another example?
So another particular project which we have really only just started on, but it's looking at what we might be able to do with trying to preserve glaciers. And there are two different approaches. Glaciers are really important when it comes to sea level rise. If we lose the glaciers on Greenland, that's 6 meters of sea level rise. And if we lose the glaciers on Antarctica, it's going to take a while, but if we lose the glaciers on Antarctica, then that's many, many tens of meters, 70 meters. So what can we do? And that's where maths comes in, as well as experimentation, and then there will be field trials as well. But mathematical modelling of trying to understand how you, for example, reduce the rate of ingress of warm saline water at the base of a glacier that's entering the ocean. Can we put a barrier up, and it might not be a full barrier, it might be what I'm going to call a permeable barrier, or a semi-permeable barrier. The idea being that we've got some modelling that can go on, whether it's numerical or theoretical modelling, as well as the physical experiments to go and then verify whether the models work or not. And then ideally going out into the field and taking measurements, which will then inform the modelling for really large glaciers. The Thwaites Glacier is the Doomsday Glacier, and that's 100 kilometres wide. And what kind of structure might you need to erect ahead of the glacier to try and reduce the rate of ingress of deep, warm, saline water? So that's one project. And then another project going on here in the Department of Applied Mathematics with Professor Jerome Neufeld is trying to understand the flow of the glacier towards the sea, and whether you might be able to intervene somehow and reduce the rate of slippage of the glacier. The classic way of doing this, in terms of that's been thought about, is by pumping meltwater away from the base of the glacier, because any meltwater at the base of the glacier, between the glacier and the bedrock, acts as a lubricant. So if you can pump it away, then that, you'd think, is a good idea. But Jerome is interested in, first and foremost, trying to understand the way that a glacier actually slips down the bedrock as a function of, for example, melt rate. And that alone is a very hard problem. But what he's finding is that there is not a one-to-one correlation between the rate of slippage of a glacier and the rate of supply of meltwater to the base of the glacier. And that begs a whole raft of really interesting questions as to what kind of intervention might be most appropriate when. Depending on the state of melting of the glacier, do you then actually say, right, I'm not going to try and pump water away from the base of the glacier, given one's understanding of how it's transitioning? If after a certain point, instead of it being a beautiful lubrication flow, well, it's not beautiful in terms of the climate, but I meant in terms of beautiful mathematical modelling, you then start to get channeling. Well, that might actually teach us that we might want to induce the formation of channels to basically let nature then take the meltwater away. If, by channeling, then the rest of the glacier then sits back on the bedrock. Yeah. Do you try and accelerate a natural process in order to try and preserve the glacier? We don't know. And these are just wonderful examples of where mathematical modelling can really help our understanding.
That was Shaun Fitzgerald talking to my colleague Marianne Freiberger about some of the fascinating research being done by our neighbours at the Centre for Climate Repair. That's it for this episode of Maths on the Move. You can also read the article that accompanies this episode by going to plus.maths.org and searching for climate repair. And for more about the maths of climate change, search climate change. Thanks for listening, and bye-bye for now.